Well, welcome back to another exciting lecture of FOR 345. We're finishing up colloids, and we're on the heels of our post-Oreo model sugar recovery from last week. I'm broadcasting in ESF TV deep in the bowels of Moon Library in this hidden studio. So now I get to talk to you, and while I'm enjoying my soils conference, you are kind of muddling through my lecture. So hopefully it won't be that bad. So the last time we talked about soil colloids, and we're going to finish up that exercise this week. And with that, remember what we've been. We've been talking about the source of the net negative charge. We talked about organic colloids. Then we went on to Phylosilicate structure, and we talked about the silica tetrahedron, aluminum octahedron. And we were left off on the silicate clay types. We classified the silicate clays based on the ratio of tetrahedral to octahedral. And in doing so, we had a little bit of fun. We had this wonderful Oreo cookie model, and it was a little bit of a sugar high, and so everyone stayed awake. Unfortunately, no sugar high right now. Oh, and recall this. So this was figure 8.8, and this was our model showing kaolinite, the smectite, vermiculite, fine-grained mica, and chlorite. And we explained the ratio of tetrahedral and octahedral sheets, covalently bonded, the interlayer spaces, and the differences in these different clay types based on the classification of these 2-to-1 layers, and based on what's happening in between, hydrogen bonding and so forth. Okay? And we left off with this table. We just were in the middle of kaolinite, and we were talking about its low external surface area, relatively low, because it's a fairly large crystal. Internal surface area, we said 0, and we said that was from hydrogen bonding. We also concluded it was not a clay that swelled when it wetted, and the average cation exchange capacity, somewhere in the range of 8 centimoles of charge per kilogram. And this had a wide range. It actually goes from negative to positive. And that was our kaolinite, and that's where we picked up. And we left off next on fine-grained mica. This was the 2-to-1 non-expanding clay. It had a slightly higher external surface area. And we also noted, so why would that be? A slightly higher external surface area means that the crystal size generally must be a little smaller. We also looked at internal surface. It was practically 0. And why was that? That was the fact that potassium held those interlayer spaces together so tightly, and there was very little capacity to have water and cations fit in between that. For the same reason, the swelling was low, and the cation exchange capacity was a little higher, based largely on the external surface. The CEC, the average CEC for these fine-grained micas, 30 centimoles of charge per kilogram, in the range of 10 to 40. Again, we're going to know these. It's be very useful in the future test. I will ask you what these average values are. So this column here for the averages is an important component of the next exam. Okay? Then we moved on to vermiculite. We said vermiculite was 2-to-1 and it was limited expansion. Okay? And it had about the same or slightly lower range of external surface area. So that means it must be the crystals about the same size as the 2-to-1 fine-grained micas. Okay. Here we had internal surface area. Now we're up to 600 to 700 meters squared per gram. And recall that this was limited expansion. Water could fit in between those layers, those 2-to-1 tetrahedral, octahedral, and not only water, but cations. So that internal surface area allows for a higher CEC. So medium swelling and an average CEC of 150 centimoles of charge per kilogram, and a pretty wide range. Okay. And now then we talked about the big expansion group, smectite. These are those clays that expand wildly. They big, large cracks when they wet or when they dry, and they shrink back up and swell up when they wet. These are 2-to-1, okay, same as vermiculite, but the expansion is quite different. Okay. And so we have not too different external surface area, okay, and we have a slightly lower internal surface area, okay, and a high swelling, and a very medium CEC. So this is kind of interesting. We have this high expansion, and why do we have this higher CEC in the limited expansion? And it has to do with isomorphous substitution. In vermiculite, the 2-to-1 expanding, it's 2 tetrahedral to 1 octahedral, most of the exchange, or most of the isomorphous substitution occurs in the tetrahedral layer. So remember that, the tetrahedral layer, that's the outside. Okay? So it is a little closer, the expression's a little closer to the surface of the layers. Okay? In smectite, most of the substitution occurs, isomorphous substitution. Most of the isomorphous substitution in smectite takes place in the octahedral layer. So the expression of charge is a little less at the surface. And that's the explanation. It's this differential location of where the bulk of isomorphous substitution occurs. Vermiculite, the bulk of that in the edges and the tetrahedral layers. In the smectites, the 2-to-1 expanding, the most of that substitution taking place in the octahedral layers. Okay. And then we had organic colloids, and they were in a field all by themselves, so to speak, in terms of their surface area. It's really difficult when you look at organic molecules to think about surface area. It's a complex concept. And so we, separating internal from external, it's kind of the whole thing. It's the whole massive surface area, and it's a very high range, okay, very high range of surface area. And the CEC for organic colloids, the average, these are highly complex organic molecules, about 200 centimoles of charge per kilogram, a range of 100 to 500. So it's pretty clear that the cation exchange capacity of organic matter is much higher. So a little organic matter goes a lot further than a little clay, much higher CEC. And so that's a pretty good thing to remember. And this really shows the importance of organic matter. And we talked about the ideal soil back in our earlier days, our first or second lecture. The ideal soil consists in pretty much of 45% of mineral material and 1 to 5% organic matter. And so that slice, that 1% organic matter, has a huge impact on the soil chemistry. If the CEC is multiple times what you get in the inorganic fraction, the clay fraction, this is kind of explains why that little bit of organic matter goes such a long way. So the other things that we talked about, we left out the last part of those colloids, the mineral colloids, and these were the non-silicates. Okay? And we had gibbsite and goethite, and the silicate non-crystallines, gibbsite and goethite, and allophane and amygdalite. That was our third category. So they have external surface area and essentially no internal surface area, and they do not swell. They're very, very stable clays. These aluminosilicate, remember they're paracrystalline to amorphous, and if we look at the CEC, they're very low for gibbsite and goethite. Okay, so those iron oxides, hydroxides, okay, gibbsite and goethite, these are fairly small. Okay, 4 centimoles of charge per kilogram. Again, we have this crazy range, plus 20 to minus 5. Okay, and say, I haven't talked about this yet, but as we conclude the session, we'll talk about anion exchange, and this may become a little clearer. It'll also be reinforced when we get to soil chemistry and we talk about the acidity. Okay. We go to allophane and amygdalite. These are the silicates, okay, the aluminums, and we have up to about 30 centimoles of charge per kilogram. Again, this wild range. So let's get a picture. Here we have a picture. So here on the left, or on the lower right, this was what something after it dries. This is 10% clay, and it's montmorillonite clay. So montmorillonite, what is that? One of the smectites, one of those 2-to-1 expanding clays. But the overall concentration of this clay, the overall texture, is very small, 10% clay in this texture. Okay? So hence, you don't see those big cracks. If we take that clay percentage, the same clay, montmorillonite, and we up it to 64%, this is a lot of clay. This is the kind of soil, what happens when it dries out. You get these very large cracks. So the amount of clay and the type of clay are very important in the physical and chemical properties. Hence, we spent quite a bit of time kind of differentiating these clays. Up here in the lower left, here's 64% clay. There's as much clay as we had above, but now we're talking about kaolinite. Okay, what were the properties of kaolinite in terms of internal surface area and shrinking and swelling? So if you remember, look back on that chart, the CEC was low, the degree of swelling was very low, it had no internal surface area, and so even though here we have 64% clay, the fact that it's this 1-to-1 clay, this kaolinite, that doesn't expand and contract, this means that we don't get those tremendous cracks when they dry. So a nice contrast to the montmorillonite above and the kaolinite below, same amount of clay, different type. 2-to-1 expanding, 1-to-1 non-expanding. Finally up here, in the right-hand side, the non-phylosilicates, remember the non-crystalline silicates, 38%, and so a little bit of expansion. And remember the qualities of that. They had some internal surface area. Okay? So all these physical properties and chemical properties can all come back to the explanation of the crystalline structure, the non-crystalline structure, the molecular structure of these. And so that's why I spent so much time kind of differentiating the 2-to-1, the 1-to-1s, and the iron aluminum oxides and hydroxides. A pretty useful thing. Okay. Now we'll revisit the exchange. So we're going to go to some of the chemistry. We talked about the ionic double layer. And remember what we said the double layer was when we introduced cation exchange? We said we could represent the colloid as a negatively charged surface. And so this is a picture of some crystalline surface. Okay? And the second layer, the adsorbed cations, things like potassium, magnesium, calcium. So there's an electrostatic attraction for these cations, positively charged ions, to this negatively charged colloid. So remember, this is the double layer, the Helmholtz layer. This is the first layer, the colloid, and the second layer is the cations. Now we're going to introduce one more thing, and a little bit of acidity, because some of these acids are quite important. And what is one of the most common inorganic acids in the soil? And you'd have to say that it has to be carbonic acid. And we've already kind of addressed this. So why is carbonic acid one of the most ubiquitous inorganic acids of the soil? And the answer, of course, is the dissolution of CO2, which is produced by respiration. So it's an important thing to talk about. And so we wonder about carbonic acid. How does it dissociate? What does it look like when the hydrogens come off? So here's the formula, H2CO3. And here's this equilibrium arrow showing the vertical direction driven to the right, driven to the left. So when carbonic acid dissociates, it puts out one hydrogen. This is actually H3O, hydronium ion, and a bicarbonate ion. H plus, HCO3 minus. Okay? It is not H plus, CO3 minus. This is bicarbonate. So it's important to recognize and remember that when carbonic acid dissociates, you get a little bit of this and a little bit of this, not CO3 minus. Okay. So let's bring that into the cation exchange picture. Here we are with aluminum, potassium, K, sodium, kind of attracted. So this is showing these particular cations attracted, adsorbed, surfacely attracted to this colloid. And with what happens when we add carbonic acid, and let's balance it. So we're going to add 3 moles of carbonic acid to this system. And what happens? Okay. So we're really adding H plus and H3O3 minus. So there's some dissociation. So now in solution, we have H plus and HCO3 minus. Okay, so this is H plus can displace some of these cations. The first one to go, for reasons which will become apparent later, is sodium, okay, Na pluses. So let's do this reaction. And we'll do Monday night cations with John Madden. Cations are in motion. There's the play. Sodium leaves. H plus is replaced. There's a big exchange. A little bit of mess on the field. Flags are down. And the end result, hydrogens have replaced sodium on the colloid. Okay? Sodium is now in soil solution, and it's associated with the bicarbonate anion. So now in solution, these sodiums are balanced by these -1 bicarbonate anions. Okay? And hydrogens have replaced sodium on the exchange complex. Okay? This is all done in a balanced manner. This week, you will be doing this in lab. If you've been in Monday and Tuesday sections, you've already done this. And you may have had a little trouble with this, but this explanation should be a little bit of assistance in terms of balancing this reaction. Neither created or destroyed can atoms be, but you have to make sure they all add up in the end. And so that brings us to cation exchange capacity. And it's not this cat. This is a picture of my cat before it became geriatric and neurotic. You wouldn't recognize that cat now, this cute little kitten that once would easily lay on the bed and purr. Now it's a mess. It's a neurotic cat that likes to chew his fur, and you never know what happened to that. But cats are strange. So let's go back to our Phylosilicate model. Again, we go back to the Marcel, the big picture. In the Marcel, we have the layers, and remember these are 2-to-1 or 1-to-1 layers you can picture. We have external surface area on the micelle, and looking at the micelle, internal surface area. Okay? And in those internal surface area, not only is there water, but there are cations adsorb. And so this greatly increases the cation exchange capacity. This is why the cation exchange capacity of kaolinite is so low and the cation exchange capacity of vermiculite is so high in smectite. There are a lot of spaces to attract adsorb cations. So let's think about CEC. So we said already, we defined CEC, the sum of exchangeable cations that a soil can adsorb, and we said this was AD, and we've always been capitalizing that. Okay? And we said it was measured in units of centimoles of charge per kilogram. In the old days, before the SI units, but still metric, the units were milliequivalents per 100 grams. Okay? This ratio of milliequivalents to 100 grams prior to the days of SI units, this ratio is the same ratio as centimoles of charge per kilogram. Okay? The same ratio, but make sure when you express it that you use the correct unit, centimoles of charge per kilogram. So we said, how do we get this? How do we understand how in the world do we quantify CEC? And here's how it's done. It's kind of an operational procedure. So we take a solution. In this case, we have a cation. This is 1 molar ammonium chloride or ammonium acetate. And we drip that solution into the soil. Okay? When something's saturated with ammonium, a high concentration of ammonium goes through the soil. Ammonium, such high concentrations, displace the cations. Ammonium essentially saturates, replaces all the cations in solution. So all those cations go out, they end up in the leachate. Now, after you do that, this is what your sample looks like, NH4 plus. And in your leachate, you have everything else. Okay? So this is kind of neat. If there's a way to figure out how much NH4 plus is in here, we have a measure of the cation exchange capacity, right? The sum of exchangeable cations. We've displaced them, we've pushed them out, we have each of those sites quantitatively accounted for by ammonium. If there's a way for us to get that ammonium, now we have a way to estimate the CEC. Pretty clever. How do we do it? Well, we leach the ammonium with another cation. In this case, the ammonium is displaced. We're going to do the same thing we did with ammonium. Now we're going to use K+. So K+ pushes out all the ammonium. All that ammonium is displaced. K+ now saturating the system. Ammonium collected here. If all that ammonium is collected here, it's a pretty simple matter to identify by titration how much ammonium is in here. So essentially, now we have the exact amount of ammonium that was held here, and now we have a measure of the cation exchange capacity. So see, this is an operational procedure. It depends on what you're using, but the idea is we're forcing all the cations out, replacing it with something we know what it is, and then replacing that and measuring what we get out. That's the trick or the method for essentially determining cation exchange capacity. Pretty slick. One of the things we think about is humus and organic matter, and we wonder how much humus, how much cation exchange capacity is accounted for. And so we have some rules of thumb. Okay? And so one of those rules of thumb, back in the envelope calculations, is that each 1% of humus contributes 2 centimoles of charge per kilogram of CEC. So how do we do that? And it's a pretty simple, straightforward calculation. It's an algebraic manipulation. So if we look at this, what's the organic matter, CEC of organic matter? We said it's an average of 200 centimoles of charge per kilogram. Okay? And you know this because now you've memorized it. You've memorized the bottom row of that table for the CEC of various colloids. And so starting with that, this is pretty easy to get to how much 1% contributes. So we take that next. For a kilogram of soil, 1% of humus, how much is a kilogram? 0.01 kilograms, okay, for 1%. Okay. For 1 kilogram of soil, that represents 0.01 kilogram of humus. Now, if we take the amount of humus in that and multiply it times the CEC, the exchange capacity, the product is 2 centimoles of charge per kilogram. Okay. So here, a kilogram times 200 centimoles of charge per kilogram. Cancel out the kilograms. See if I can get my pen. Like to play. And there we go. Kilograms here. Kilograms in the denominator. And the units that we end up with, centimoles of charge. Okay. So let's expand that. Suppose that average CEC, the number was better. We got an actual number in that range. Remember, the range is quite wide. Suppose the CEC we measured was 300 centimoles of charge per kilogram. What is the contribution of organic matter? Could you go through the same calculation? Okay. And so be sure you can do this for the others. So this week in lab that you're taking, you have gone through, or you will be asked to come up with a CEC given various types of colloids in various proportions. So this is essentially the thought process. This is the calculation. This is the way to get to that answer. Okay? And so this will help you execute lab this week. Again, if you're Monday, Tuesday, you've already done it or haven't. And if you're Wednesday, Thursday, Friday, this will be a little easier calculation for you. Okay? Now we get to the source of the net negative charge. We kind of started talking about this. We talked about isomorphous substitution. Okay? So the silicate clays, we explained the substitution of aluminum +3 for silica +4. Okay? And so what's that mean? Take aluminum +3 and you put it in a tetrahedral of silica +4. What is the net negative charge? Now you're putting in that crystal, you've got a -1. Okay? So the more substitution in the silicate layer of aluminum +3 for silica +4, the greater the number of charges, the greater the net negative charge, the greater the cation exchange capacity. Okay, ... That's in the tetrahedral layer. In the octahedral layer, there's aluminum. Remember aluminum +3, the octahedral layer? Okay, the dioctahedral layer. If magnesium +2 substitutes for aluminum +3, the same result. That's -1. Okay? So every time that substitution happens in that octahedral layer, we get more, and the cation exchange capacity increases. Higher net negative charge expressed at the surface. Okay. What about iron aluminum hydroxides? Okay, so that's one mechanism, silicate clays, isomorphous substitution. So iron aluminum hydroxides, and the mechanism is a bit different. Okay? There is no substitution in those. Okay? They are kind of they are amorphous to paracrystalline, maybe to crystalline, and we don't have those nice crystal structures as we do with silicate clays. So the idea, the reigning paradigm for the source of that net negative charge in the iron aluminum hydroxides, exposed crystal edges. Exposed crystal edges. So that's, what does that mean? Well, it means exactly what it says. If you visualize these aluminum oxide hydroxides, okay, these covalently bonded, and if you get these edges and you get some breakage, you have H+ dissociation. Okay. So here it is, H+. Now, these are only external, and they're pH dependent. So it's another reason why those numbers are so small for the iron aluminum oxide hydroxide. It's very low CEC, very stable. Okay? The only place, the only source of that dissociation of H+, the source of H+ for letting the cations replace those, is these broken edges. And that's an external, and these are rather large pieces. So it's a small number. Okay, so that's a contrast. That's a contrast from what we just talked about. We just talked about substitution, okay, in isomorphous substitution in the silicate clays. It contrasts the iron aluminum hydroxides, exposed crystal edges, okay, dissociation of hydrogen rather than isomorphous substitution. Net negative charge. Pretty picture. Someone ask, or might ask, or might think, well, this doesn't seem, why is it that aluminum substitutes for silica and magnesium substitutes for aluminum? And now we're getting down into the molecular answer, and it's because of the atomic radius. Okay? So the atomic radii in angstrom units for silica +4 is slightly smaller than aluminum +3. Okay? The magnesium +2 atomic radius, 6,6, is slightly smaller, or slightly larger than aluminum +3. Okay, because of these approximate sizes, aluminum is the right size covalently to fit in there in terms of its molecular size, It's just about the right size, so it can get in there and it can fit. It fits in that space in the tetrahedral sheet. So the same is true for magnesium in the octahedral sheet. Magnesium can sub there. Okay. It's another, iron plus can't substitute for silica plus 4, iron plus 2. It's too large. Okay. Calcium is too large, so it's all about ionic size, okay, ionic radius. And the same with the aluminum octahedra. You can get some iron in the aluminum octahedra, but these within this range will substitute. The dominant substitutions are alumina for silica, okay, and magnesium for aluminum. They aren't the only ones. They are the dominant ones and the ones we usually talk about. There are some others. You can get some iron plus 3, okay, but not iron plus 2 going into silica. And so this is the range, and these are the dominant ones. Okay. We'll just worry about the dominant ones, but just to make you aware that it's not just those. There are things that are close to size that can also substitute. Okay. You'll recognize these as exchangeable ions. So the exchangeable ions, electrostatically attracted, okay, think about those in a different form. In this form of isomorphous substitution, we're thinking about covalent bonding. When we think about exchange sites, we're thinking about electrostatic bonding, electrostatic attraction, adsorption. Okay? So it's important to keep those two separate. So let's do a practice quiz. We have a reaction, a calcium, calcium K, calcium, calcium K, and we want to balance this reaction. So if you take the complete replacement and you add hydrochloric acid, how much hydrochloric acid does one have to add to counteract this amount of these nutrients? So what's the first step? The first step is sheer panic. Not really. This is a very simple thing. So the first step, how many positive charges? Okay, so here you have to have some knowledge. Okay, so you need to know that calcium's plus 2. All right, and you need to know potassium's plus 1. Okay, let's do the charges. Calcium to calcium. 2 plus 2 plus 2 plus 2. 8 calciums, 2 potassiums. So that's 10. 2, 4, 6, 8, 9, 10. So there's a total of 10 positive charges. So that must mean there's negative 10. We have to satisfy 10 sites here. Okay. So how many positive charges? 10. So how does HCl break up? How does that dissociate? So you should recognize that's a strong acid. And so this dissociates, you get into H plus and Cl minus. I feel like I'm doing a Calvin and Hobbes cartoon. Okay. So how many hydrogens do you need? Well, what's the valence of hydrogen? Plus 1. All right. So that means you must need 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this balances. Next question, what do you have out here in solution? You had HCl. What's out here in the soil solution? So I guess the stuff that comes off here, it doesn't disappear. And remember, this is exchange. So this goes out in the soil solution. And we have calcium and potassium. Okay. So the last thing is, we have chlorides. What is the balance for chloride? Okay, it's minus 1. Okay. So for every calcium, you need 2 chlorides. Right? Calcium is plus 2. Potassium is plus 1. Right? So there we go. And then the question is, the final balance, how many calciums came off? 1, 2, 3, 4. So there's going to be 4 calciums. Okay. How many potassiums came off? 1, 2. Okay, so I'm going to put 2 potassiums. Okay, now is the rest balance? Let's see. I have 4 calciums. Okay, 4 times 2, 8 chlorides. Okay, plus another 2 chlorides, 10 chlorides. Okay, so that's okay. I have 2 potassiums. That's okay. So that balances. I have 4 times 2. Yep, everything balances. So now I've checked both. So the first thing is the number of charges. Second thing is what's coming off. Third thing is balancing the subscripts. And then lastly, balancing the molarity of the materials coming in, or the amount. And that's pretty straightforward. And it checks out. Very good. Okay, now let's switch to the acid. So here's a question for you. This is a take-home. Okay, take the same problem, calcium, K, and now the question is, how much carbonic acid do you need to make this reaction go, and what does it look like? So this is a take-home, and I will ask you next Monday what your answer is. Okay, and you should be able to do this because you're doing it in the lab. And if you can't do this after the lab and can't come in Monday with this done, then there's something wrong. Okay? Or maybe you just partied too hard and had a rough weekend. Let's hope not. Now, I had those ranges. We talked about the iron aluminum oxides and hydroxides, and it was funny. I had a low CEC, but I had a range that went from positive to negative. Say this is, I'll explain this later. Well, the time has come. Let's go picture that. Here's our slide. We're looking at aluminum oxides, hydroxyls on the edge, and we're looking at the edge. And occasionally, instead of having a hydrogen dissociate, okay, you can have a hydrogen attracted. Now this happens when there's a lot of H plus around. So when is there a lot of H plus around? High acidity. So when you have very acid situations, very acid solutions, you actually can have hydrogens being attracted to these hydroxyls. And this creates a positive charge, a net positive charge. This is why I stressed pH-dependent charges. We're looking at the other side of that. We stressed that from the negative side. Now we're stressing it from the positive side, pH-dependent charges. Under conditions of high acidity, and here's what that looks like all put together. At these broken, here I'll draw the broken crystal edge. Pretty slick. Positive charges, high acidity, pH-dependent charge. This is the other side of that story. So that leads to one more thing. If we can have positively charged colloids and low acidity, what can happen? We get anion exchange. So anions, negatively charged ions, move around just like cations. And if we have a colloidal surface that happens to be positively charged, those negative anions are attracted to the positively charged surface. Same phenomena, but now we're dealing with anions. So instead of cation exchange, anion exchange. The same thing in a different direction. Again, keep in mind that the pH-dependent charges are an important part of this, and that's why we stress that in terms of pH-dependent CEC. So we go back to nitrate. So here's a soil colloid with a positive charge, net negative charge, must be acidic conditions, and nitrate is adsorbed. Okay, this is an anion, so this must be a net positive charge. It's depicting one of those crystal edges, broken crystal edges under high acidity. Okay, and so here's in the soil solution chloride. Okay, so we have chloride in the soil solution, and chloride, just like the cations, can exchange for nitrate. Instead of a cation exchange, there's an anion exchange. Nitrate into solution, and you can do the same kind of balancing. And what do we think about that? Well, we think about there are certain colloid types that are prone because they can have a net positive charge. And those are them, the iron aluminum oxides, hydroxides, and the silicate, the silicate non-crystalline allophane and amogolate. So these four, those colloid types, can actually have a positive charge under conditions of high acidity. Okay. And that leads to anion exchange. So that's kind of neat. And that leads us to, well, are some cations more attractive than others? Some people are, and cations are no different. Well, they're a little different. And so the explanation for this has to do with the hydrated radius. So the strength of attraction for colloids, for these cations, has to do with how big the radius is in solution. And the two factors are valence, +1 is low, +3 is high, right? That's valence, and hydrated radius. And here's the sequence. Aluminum +3 is much more strongly attracted than calcium +2, is more strongly attracted than magnesium +2, which is more strongly attracted than K+, which is about equal to ammonium, NH4+, which is more than sodium. So sodium is the least attracted, aluminum is the most, and it stair steps down in this sequence. And we go from a very tight, high valence to a lower valence, to a lower valence, and finally to a very large hydrated radius. So what do I mean by hydrated radius? When a cation in solution is floating around, it's not just the cation. Okay? So cations in solution float around with water. Water is a polar molecule, and the negative ends of the electronegative ends of the water molecule align themselves to surround the cation. Okay? So you've got this cation, and if you have a very large valence, +3, the attraction for water is very tight. So aluminum +3 has a very high attraction for water, and when aluminum +3 travels in solution, the water shell around it is very tight and compact. So you have this real tiny physical space, and so aluminum is traveling around. Okay, sodium, on the other hand, has a very large hydrated radius. The very low valence means that it doesn't attract the water molecules strongly. So when sodium floats around in solution with its hydrated radius, the water around it, it's this bigger moiety. And so here you have sodium floating around, okay? And here you have aluminum. Aluminum, nice, tight, compact. This aluminum floating around will satisfy 3 negative charges. This big sodium behemoth will only satisfy 1 negative charge. And so you can physically fit a lot more of these aluminums in close proximity to the surface of the colloid because it's tight and it satisfies a lot of charge, compared to sodium, which are physically large, unwieldy, and you can't get enough sodiums around these to actually counteract the charge. You still have a net negative charge, it's just too big and unwieldy. And that kind of plays out in some of the things we did for soil texture. How do you overcome that? Mass action. That is, even if I have a solution of sodium, and I can overcome attraction by having a very high concentration. So concentrations in the soil are millimolar. If I take sodium or ammonium, which is not very strongly held, and I can displace aluminum, which is strongly held, simply by mass action. If I take a 1 normal solution, high concentration of ammonium or sodium, and I flush the system, even though aluminum is tightly held, the concentration gradient will force the tightly held cations off of the colloids. So it's pretty interesting, and that's the concept of cation exchange. We think back to our cation exchange addition. We leach the soils with ammonium. We took that ammonium, and even though ammonium isn't really strongly attracted, and aluminum is, all those ammoniums will overwhelm the relatively few aluminums. It's a concentration gradient, mass action. And that's how we can allow to get cation exchange. Even though aluminum, all things being equal, concentration-wise, much more tightly held, much more tightly attracted to the soil colloids than sodium or ammonium. Here's a picture. Okay? So I did it with my hands. Here's a picture from the text, and it shows that same concept. Okay? Here we have sodiums. Okay? And potassiums, and so the micelle, and you see the relative size of sodium and its hydrated radius in green. Get rid of this pen, get a pointer back. Let's see, arrow options. I don't know, I think I might have missed. There we go. Here's sodium, and here's its hydrated radius. Relatively large space taken up around the micelle. Same with potassium. Okay? Roots are exuding hydrogen ions. Here's the same case with aluminum. Okay, so aluminum, very tight. So you can get these aluminums, this same physical space, aluminum, in this small space around the micelle. This is satisfying 3 charges. Sodium, this larger space, only is satisfying 1 charge. Okay, so you can see why these are more tightly held and these are attracted to the micelle more strongly. And so let's go back to that. We're going to add one more piece to that, aluminum +3 and sodium +1. So things that have a high valence and a very tight hydrated radius, very small hydrated radius, these are flocculating agents. So when you have a lot of aluminum in solution, so a flocculating agent will cause clays to clump. A dispersing agent will cause clays to stay in solution. So aluminum +3, which is very tight, rapidly moves. If you have aluminum in solution, and you do this in your lab this week, aluminum solution, you add aluminum +3 to solution of a clay, the clays will flocculate. You will satisfy the net negative charge because of the very small hydrated radius. As opposed to sodium, it has a very large hydrated radius, only satisfies a single charge. And so if we use sodium in the system, it will maintain clays dispersed. You cannot physically fit sufficient sodium around the clay in solution to overcome the net negative charge. And we took advantage of this when we measured texture. When we measured the texture, we used sodium hexametaphosphate as a dispersing agent. This ensured that the clays stayed in solution and didn't flocculate. Had we made a mistake and given you aluminum hexametaphosphate, that would have been quite a disaster, right? Because aluminum would have clumped all those clays, they'd all fall out of solution, and you would have no idea the clays were in there because they would have been mistaken for sand or silt as they fall out. So flocculating agents, small hydrated radius, high valence; dispersing agents, low valence, very large hydrated radius. Here's a question. Ammonium chloride, 1 normal solution. How many centimoles of charge does a 1 normal solution of ammonium chloride produce? And that's what I'm going to leave with you. So now we have a pretty good picture of clay chemistry, the silicate clays, the non-silicate clays, the oxides, hydroxides, and the organic colloids, and a pretty reasonable understanding of why their chemistry acts as it does. And so we'd like to put that together in a bigger picture and think about the genesis. How are silicate clays made? Where do you find them? And how are they distributed across the globe or across various climatic regimes? So that's the next thing we'll think about as we'll talk about the genesis of silicate clays. Where do clays come from? We know that silicate clays come from aluminosilicates, those primary minerals that we talked about at the beginning of the course, things that had aluminum and silicate. And they are altered. And so the alteration, the weathering of silicate, of the aluminosilicates generates silicate clays. So there's weathering that's light and not intense, and there's weathering that's very intense. And so you can actually have just alteration, making things smaller or making some slight alterations in the crystal, or you can actually break down and recrystallize. So this goes from relatively light to relatively intense weathering. And so that brings us to mind, if we think about if we can do a light weathering or a heavy weathering, an intense weathering, we could think about the genesis of silicate clays relative to the weathering sequence intensity. And here's a depiction of charges on clay colloids, centimoles of charge per kilogram, and by weathering intensity. So mild weathering intensity might be light rainfall or mild temperatures, and a strong weathering intensity would be high temperatures, high effective precipitation. Think about tropical rains, tropical systems. Mild might be, think about the Midwest, light rain intensity, relatively moderate temperatures, and then intermediate. And so this is our charge, our CEC. We go on colloids, we go to +20 to -40. And we talked already about why we have positive numbers, okay? Positive numbers in the iron aluminum oxides because of this low acidity situation. So if we look at the mild weathering regimes, we have cation exchange capacities rather high, okay? And as we increase weathering intensity, cation exchange drops, okay? And in fact, we get into anion exchange because we get into the removal of silicates, the iron aluminum oxides and hydroxides, the very highly weathered clays. So this is highly weathered system. This is mildly, slightly weathered system. And the relative cation exchange capacity goes down with weathering. and the anion capacity goes up, and because in these intense systems you have very high acidity. So let's look at that from another viewpoint. Let's start with the primary minerals, and this is out of the text, figure 816. And we have primary minerals that are high in potassium. Microline feldspar, orthoclase feldspar, muscovite, some of the micas. And then we get high in iron, magnesium, calcium, things like biotite, chlorite, which is a primary mineral, soda lime, feldspars, hornblende. So, and we already looked at these, right? We had the characteristics of these. We said the orthoclase was a potassium feldspar, muscovite was a mica that you get potassium from, and so forth. And biotite was this, you get iron. So we've already reviewed what are the essential elements. Now we're going to think about them in terms of clays. Okay? So all these materials can produce clays, some of the silicate clays, and let's look what happens. So if we just take rapid removal of bases in weather, okay, we can get to some of these microline orthoclase. These are primary minerals, and we remove the magnesium, the potassium, and so forth very rapidly and intensively. We can get the kaolinite. Okay, so if we remove them a little less intensively, we can get the smectite, okay, and the vermiculite. So remember vermiculite, this slightly expanding. If you start to weather that, you can get to montmorillonite. Remove the silica, and finally get the oxides. So this last column, oxide, these are very intensively weathered, okay? And you can get them from alteration, then hot removal. So this is very intense, requires some really heavy-duty weathering, okay? Successive removal of silica. What you start with can influence what you get early on. So muscovite will produce the fine-grained micas. Okay. And so here's illite. So as you remove more and more potassium, you can get the smectite. So that's an alteration. And as you remove more and more silica. So it goes in steps. And so early on in the weathering sequence, the materials look an awful lot like the parent materials. The parent materials make a big difference. But as the weathering sequence becomes more intense, the parent material matters less, and ultimately in a high weathering sequence, you end up with these oxides of iron and aluminum. Okay. What's some of the measurements, some of the indicators? One of the indicators of these heavily weathered soils is a low ratio of silica to aluminum. Okay? And we use that as an index of weathering. And why is that? So silica is soluble and is removed, aluminum builds up. So as you weather more intensely, you reduce the silica and you increase the aluminum. Okay? What does this mean? This means the ratio of silica going down, aluminum increasing, this ratio goes down. So this is often used as an indicator of weathering intensity. So we kind of wrap up some of that with a limerick. There once was a cation called Na that hydrated in a large sort of way. Applied to fields made things worse. As the PEDs did disperse, but for texture it gets the okay. So that should make some sense. How about another one? There once was a cation called Al. For flocculation, it seemed to excel. You should know this from lab. Put in bentonite suspension. Remember what bentonite is? 2-to-1 expanding clay. Permitted no retention. As the aggregates to the bottom so fell. By colloids. That wraps it up for colloids. We have all that material taken in lab. This should all be integrated. So this is an important step to think about. So we've just completed, or in the process of completing, the soil colloid lab, CEC. You've gone through the calculations and the questions. So all the material covered in lab, it's the practical application of all the concepts we've had in lecture. So these two things merge one-on-one. So as you prepare for the next test, try to understand, and as we move toward the final exam, it's a key importance that you address both the lecture and the lab material and kind of use the text to fill in. So you should be thinking about that rather intensively. The second thing is this sets us up nicely for soil acidity. So soil acidity is the next to last unit, then we get into fertilization and fertility. As we talk about acidity, we'll reinforce some of these concepts we've discussed. We'll talk about pH dependency, and we'll bring this forth a little further and kind of build on that. And we'll also bring into the factor aluminum and hydrogen and their interactions. So that's next. And so with that, I'm going to let you go a few minutes early, and I hope that you've had a good week. I'll be back from the Soil Science Society meeting in another day or two, and I will catch up with you. We'll have our usual review session on Friday. I hope to see you there, and have a good week.